introduction, and thank you very much for the invitation and for organizing this workshop. So I'm going to talk about the joint work that I did with Thomas Hillen and Henri. So the idea of this work started during my PhD when Thomas Hillen suggested to enrich this rather well-known model, M5 model for cell migration by contact guidance with a direction-dependent turning rate. So we are talking about cell migration on the fibers of the extracellular matrix. So fibers reorient and move by contact guidance. That means that they crawl on the fibers of the extracellular matrix, and they tend to assume the direction that is parallel to the fiber that they are walking on. So Thomas suggested that we could improve this model by adding this, as said, direction-dependent turning rate, because the main idea is that if a cell is already aligned along a fiber, then the frequency of orientation is lower, while if it is traveling perpendicularly to a fiber, then the turning rate should be higher. And in particular, if we need to improve the remodeling in our model, then cells traveling perpendicularly to a fiber then actually do not reorient, but tend to cut the fiber if we want to include proteolytic mechanism. Then we also observed that Hillen's model could not include, could not describe persistent random walks in symmetric environments. That means that if the fibers are not polarized, we can biologically observe persistent random walks, but Hillen's model was not able to reproduce them. And then Henri showed us this very interesting experiment by Doyle, in which, in which there are fibroblasts migrating on fibronectin stripes. So, do you see my video? Sorry.
Yeah, we see the video. Now it's stopped, but we see it.
Okay, so in which they show the contrast between absence of fibronectin stripes and this crisscross configuration that is an anisotropic configuration. But they observe that in the empty configuration, fibroblasts diffuse really slowly, while in the crisscross configuration, the diffusion is much faster. So the problem is that Thomas' model, even if it was applied for a wide variety of applications, could not reproduce this difference between these two anisotropic settings in which the diffusion is very different. So let's go back here. So just few words, no? One. You're supposed to see here? Okay. It is a video. Okay. Okay. So just few words on Thomas' model. So it is a kinetic model for cell migration. So fibers, the presence of the fibers of the extracellular matrix is described through the introduction of a probability density function to eta that's parameterized by time, position, and direction of the fibers. And the cell population is described through the introduction of a distribution function P, parameterized by time, position, and velocity W, that belongs to a compact set. In this talk, we shall consider fixed speeds, but we could consider any compact set. So the time evolution for P is described by equation 1, here that is a classical transfer equation, in which in the left-hand side we take into account for the free particle drift, and on the right-hand side we have the turning operator that implements the scattering of particle cell, so that drives the turning of the cell due to contact guidance. So it is classically written in this way. So we have a mu frequency of reorientation and a turning kernel Q that is a transition probability. So a transition probability of switching from W prime to W. So the main assumption is that Q does not depend on the incoming velocity, but it also depends on the new chosen velocity W. positive and it's an error function, actually a probability density function. And the very simple idea of this model was to relate the term for the transition probability fibers distribution because cells tend to assume the direction of the fiber. So actually, Q is equal up to some noise constant to the probability density distribution of the fibers. So thanks to hypothesis A1 here, we have that our Turing operator rewrites in this very simple form as in. So we can recover a macroscopic expression by introducing a statistical quantity, for example, average direction imposed by the fibers and the matrix of the variance covariances. And we can do the same thing for the cell population by introducing the moments of P. In particular, we can introduce the cell macroscopic density, P bar, and we can also introduce the moments of the normalized population, P hat, so as to recover the average velocity and the variance covariance matrix. So thanks to the definition of star P, so the macroscopic cell density, we may rewrite our Turing operator LP in this way. So we have here our Turing mu and this same term that's given by the product of the macroscopic cell density and the fibers distribution. And we also can see very, very easily that the Maxwellian of the systems for the local asymptotic equilibrium is given by the transition probability itself, so by the fibers distribution. We also have that if we perform a diffusibility of this kinetic equation, then we have this fully anisotropic macroscopic model that was applied, for example, by Hillen and Painter for describing the diffusion of glioblastoma by relating this variance covariance matrix to the DTI tensor of the brain. So now our idea was to start from this kinetic model and to include in the Turing frequency a dependence on the position and in particular on the velocity, the microscopic velocity of the cell. Therefore, we need to rewrite our Turing operator in this way. And the very simple assumption that we added is that both mu and Q over mu are L1 function. In this way, we can inherit very easily many results concerning the linear Boltzmann equation that I do, for example, with Peterson, Hugo, and Legrand, concerning existence and uniqueness and the H theorem, so as to find the Maxwellian of the system. So it is very useful to introduce other statistical quantities. So in particular, we can introduce the Turing part of the population that's given by the function P mu. And in particular, we can introduce the moments of P mu so as to obtain the macroscopic density of the total Turing population and its average velocity. In this way, we can rewrite our Turing operator in a more compact form in this way. So we observe that here it is different from the one that we showed before. So here we have mu that appears explicitly only in the loss term, while it is encoded here in this macroscopic cell density of the Turing population in the gain term. And what we can observe is that we have conservation of cell density, but we have not conservation of the momentum because we have, in this case, active particles, so active cells that move by contact guidance. If we look for the equilibria of the system, then we have to study the kernel of the operator L, and we find that population phi nullifies L if it is proportional to Q over mu, where here times the macroscopic density of its Turing part. And it may also be rewritten as its macroscopic density times T, where T is a probability density function, here defined in 6, where C is a normalization constant, so it's actually the integral of Q over mu. And it may be seen as the distribution of run times along the fibers described by Q, because 1 over mu is the turning rate, and therefore 1 over mu is the run time between two consecutive reorientations for a cell having velocity w. Therefore, as t is actually a probability density function, it is our Maxwellian, we can introduce its average velocity, that is the average velocity of the Turing population over the fiber distribution. And this quantity may be also be rewritten in this way. So if we introduce chi, it is the displacement for a cell having velocity w, then we may also integrate this quantity in order to obtain the average displacement for a cell over the fiber network. And therefore, this average velocity of the fiber distribution is given by the ratio between this mean displacement and the mean runtime c over the fiber network. We can also introduce and generalize previous definition of directional persistence. So the persistence is meant as a measure of a random walker's tendency to maintain direction during directional changes. So if a cell is identified with its microscopic velocity w, then we define its persistence by projecting this microscopic velocity over the mean velocity of the equilibrium distribution t. Therefore, we defined it as in 8. So this persistence is given actually by the cosine between the angle between w and this average velocity of the Turing population over the fiber network. So this quantity ranges from -1 to 1. So 1 means perfect persistence, while -1 means perfect reversal. So we have that if mu does not depend on the microscopic velocity, so the whole case, then we have that we obtain the whole definition that was given by Hoffman, Alt, and Goodman of the directional persistence. And here we observe that if Q was a given symmetric, non-polarized distribution of fibers, then Q is a null function, and therefore we have no persistence. In this case, in H, if Q, even if Q is completely non-polarized, so Q is an infinite function, then T may not vanish because we can include some persistence in the Turing frequency. Then what we did, we investigated macroscopic limits. In particular, here we present the diffusive limits of this equation. So we consider assumptions listed before, and we assume that this average velocity actually vanishes. So we consider our kinetic equation rescaled in a diffusive sense, and we consider a Hilbert expansion of our distribution function P. And we have that the leading order term satisfies this relation. That means that so all the mass is in the leading order term, and it is proportional to the Maxwellian T of our system. So T that was given by 2 over mu. And this macroscopic cell density satisfies this macroscopic and isotropic diffusion equation, where this dt is a microscopic and isotropic diffusion tensor that's given by this quantity. So in order to prove this theorem, we consider our distributed equation and expansion, and the main work was in inverting the operator L. So L is defined over L2 space, that's on which we define a special scalar product with the factor eta that's given by mu over t. So we have already seen that the kernel of this operator L is spanned by t, while the range of L is spanned by the orthogonal space to the span of eta to the -1. What is this space? This space is actually made up of all the populations that have 0 macroscopic density. And therefore, we invert our operator L from this space to the orthogonal of the kernel of L that is made of the cell populations that have a 0 macroscopic Turing part. We We can also rewrite our macroscopic equation in this way. So just by using applicating the quotient rule, we find this equation 12. That is a grid diffusion equation. So we have a diffusion tensor that's related to T over mu, and an advection term that describes the fact that cells tend to move towards decreasing values of the turning frequency. So what does it mean? So in order to understand the roles of Q and mu on the overall dynamics separately, we have analyzed the diffusion equations that concern these active cells, and we have tried to compare it to known diffusion equations for passive particles. So we start for a moment from the case in which mu does not depend on the individual velocity, and we consider the case in which Q, so the heterogeneous case, in which the turning frequency only depends on the special variable. So in this case, we have this fully anisotropic process with advection that, as said, leads to decreasing values of the turning frequency. If we consider a constant turning frequency, then we only obtain this fully anisotropic equation, while if there is not at all heterogeneity in the special case, then we obtain this Hillen form. So this is actually the classical diffusion equation. In a heterogeneous environment, we only have a source of anisotropy that is linked to the fibers distribution. If we add this entering the fibers, then we obtain this equation that's similar to the Chapman equation for heterogeneity in the space. While if we go to this more complex mixed structure, we recognize the derived equation that was derived for describing diffusion in a heterogeneous environment with a thermal effect. So we can actually compare our turning frequency to this temperature that describes adaptation to the environment. And we can, in a biological sense, compare it to the starvation mechanism, according to which biological particles or cells tend to escape from situations where they tend to starve. If we try instead to look what happens in the full case, so when mu depends also on W, to isotropy and anisotropy, we go back to our drip diffusion equation and we observe that U T equal to Q over mu. Then we have that our diffusion tensor is given by this formula. So we have that if Q is proportional to mu squared, then we have isotropy. While if Q is only proportional to mu, that is stronger here, then we have non-persistent walk. And in general, an anisotropic diffusion, while if Q is proportional to 1 over mu, then we have an even stronger anisotropy. So in order to visualize this, we consider some numerical tests. So we integrated the kinetic equation in a 2D setting. In particular, we considered this fiber distribution that's given by a bimodal for Mises distribution. So where here theta is the average direction and k is the alignment parameter. In particular, we shall consider these two settings. So in the first one, we have fibers distributed along pi curve and k that is in the center of the domain. In the second set of simulations, we shall see these cross configurations in which fibers are only on the arms of the cross. So if we consider this distribution of fibers along pi 4, then we have that if mu is constant, then we have, of course, an isotropic diffusion along pi 4. While if mu is equal to Q, as pi 4 now is also the direction of highest turning rates, then we have that the diffusion is in the orthogonal direction pi 4. And this is because mu here is stronger in the definition of the diffusion tensor. Then instead if Q is equal to mu squared, then we have both diffusion in the direction pi 4 and in the orthogonal direction. So we have this kind of strange isotropic diffusion. On the other hand, if Q is constant, so if there are no fibers and we try to investigate only the role of this direction-dependent turning rate, and so we have that mu is distributed over pi4, so pi4 is again the direction of the highest turning rate. Then we have that cells tend to go away from the center, because in the center, in all these cases, there is the highest turning frequency, and they tend to go away from this position, but in the orthogonal direction to pi4. Something similar happens in the cross configuration. So if we consider that fibers are horizontal on the horizontal arm and perpendicular on the perpendicular arm, then if mu is equal to Q, that means that these directions are also the directions from which cells tend to escape the most. Then actually cells do not pull on the fibers. On the contrary, if the average reaction of the turning frequency is perpendicular to the one of the fibers, then cells tend to go on the arms of the cross, because these directions, the perpendicular one, are also the ones that correspond to the smallest turning rates. So now we go back to our Doyle's experiment. So we consider the two settings, so the one in which we had an empty region and the one in which we had a crisscross region. So we describe the setting A with an isotropic distribution of fibers, and setting B with this combination of a two bimodal formulations distribution in order to have this crisscross region. So the classical Hillen model here would not predict any difference. So we would have the same macroscopic isotropic fluid anisotropic equation. If we choose this direction dependent turning rate, that's proportional to 1 over Q, that means that cells that are already aligned do not have a high turning rate. Then we find this isotropic diffusion, of course, but the diffusion coefficient depends on the alignment parameter. In particular, we have that by increasing the alignment parameter, we have a stronger diffusion coefficient. And we can show it also with numerical tests, again, of the kinetic transfer equation. So here in the first line, we observe case A. So here there are no fibers, and cells do not really manage to go across the domain. While here, if we increase, so we consider this direction-dependent turning rate, and we increase our alignment parameter, we have that cells manage to go across the region, the crisscross region, and by increasing the alignment parameter, the speed with which the cells go across the domain is also faster. So, and I have finished, and I thank you for your attention.
That's always the purpose of the conference. Are there any questions online? In the room, do you have any questions?
Yeah, we have a question in the room.
Okay, ask it.
Thanks for the great talk. I was wondering what method you use for the numerical simulations.
Yeah, okay. Well, I actually used numerical method that was proposed by Hillen. Torino work. No, it's not here in the bibliography, but it's actually, I considered, so I go back to the equation so that it's more clear. So you actually consider a splitting. So I perform the spatial transport and then the relaxation. For the spatial transport, actually it's just a transport for each microscopic velocity W, and I use a van Lier scheme, so a flux limited scheme. And then for the relaxation, I used an explicit scheme, because here you cannot use some like the classical results, as you don't have. You only have conservation of mass, and in particular here, P does not appear explicitly. You cannot use an implicit integration, so it's just an explicit integration of the turning operator. and have specular-reflective boundary conditions.
Thank you.
Okay, thank you. I don't think we have other questions in the room.
So maybe just one quickly, because we're already very, very late on the schedule.
Yeah, we don't have.
We anticipate that we'll be delayed again for setting up the next presentation.
Okay, for here we're set. So see if you have something on the chat.
Okay, so if we're set, so we're gonna thank Nadia again.